Right, so if you completed the Desmos activity, this is going to be a really easy lesson, right, because you've already discovered what I'm going to be teaching you. I'm just going to add a little something to that lesson so that we can use transformations, which you learned in the Desmos activity, to be able to graph quadratic functions another way. And now, we won't be able to use this for every quadratic function, but some, right? And so it's a very helpful tool to have, and we'll graph a lot of other functions this way as well. So a transformation is an operation performed on a function that moves every point up, down, right, left, or dilates the function, or reflects the function. Right? So adding a number to the whole function or to x translated the function up, down, right, and left. If we had a coefficient on x squared, it can dilate the function. It will dilate the function. It can make it wider or skinnier, or can reflect it. So a parent function is the general form of a function for that degree polynomial. It's the simplest function for that particular degree. And degree is just equals exponent. So whatever your exponent is, that's your degree. You don't need to write it in your notes on this lesson because we'll write it in on a future lesson. Right? So the degree is equal to the exponent. Now what happens if a term has more than, what happens if an equation has more than one exponent? Well, it's the largest if there's more than one term. So some common parent functions, and all of these will be graphing, this and more. Except for actually 0 and 1, you already did that in Algebra 1 and Geometry. So this is just the exponent, right, and another color besides blue. This is just the exponent on x. So if we have x raised to the 0 power, right, that's just anything raised to the 0 power is just 1. Right, and that's going to give us a constant function. A constant function graphs as a horizontal line. Right, and the parent function, f of x, equals c. F of x or y equals c. If we have x raised to the first power, we have a linear function, and the parent function is f of x equals x. If we have x raised to the second power, we have a quadratic function. And the simplest function, the parent function, f of x equals x squared. In a later lesson, we'll be graphing other polynomials, x cubed, x to the fourth, maybe even some x to the fifth. But let's just use x cubed. Right? So x cubed is a cubic function. The parent function would be f of x equals x cubed. Of course, if the degree was 4, then the parent function would be f of x or y equals x to the fourth, and so on. Now, you're probably not used to seeing fractions as exponents, right? But if you think about it, right, 1/2 is the multiplicative inverse of what number, right? Of 2, right? Because 2 times a half would give you 1. So what's the inverse of squaring? Taking a square root, right? So squaring, and so a degree 2 and degree 1/2, they are inverses of one another, right? Because if we take the square root of an x squared, right, we would be undoing that squaring, right? So x to the 1/2 is the same as the square root of x. And you will learn how to change between, this is called a rational exponent because it's a fraction, how to change between rational exponents and radicals in a future lesson. So that's the square root function. Of course, the parent function would be f of x equals the square root of x. If you have a negative exponent, that just makes the term the reciprocal. Right? So x to the negative 1 is the same as 1 over x. That's called a rational function. Rational just means fraction. Right? And our parent function, f of x equals 1 over x. Right? So these are just some introduction to some common parent functions. We are going to be talking about, however, just this one. Actually, I will show you absolute value in here as well, just because it's another function that I can use to demonstrate translations with and dilations, and is very similar to a quadratic. Has a vertex and everything. All right, so transformations in graphing. By performing operations on f of x, the graph of f of x will shift or slide. This is called a translation. There are 4 types of translations: horizontal translation, vertical translation, reflections, and dilations. All right, we're only going to be looking in this lesson at horizontal translation and vertical translation. And I may actually split it into 2 videos. 1 video for vertical, 1 video for horizontal. Because we're going to start with vertical. All right, so vertical shifts. This is the first thing in your notes, and it's already in your notes. So let f be a function and c a positive real number. The graph of y equals f of x plus c. Right, note that c is not added to x. It's just added to the whole thing. Right, so no parentheses. Is the graph of y equals f of x shifted c units vertically upward. The graph of y equals f of x minus c is the graph of y equals f of x shifted c units vertically downward. And it doesn't have to be a parabola. This would be true for any function. If we add something to the whole function, it's going to shift it up. Whatever we add to it, that's how far it's going to shift it up. If we subtract something from our whole function, that's how much it's going to shift it down. So this is already in your notes. A vertical shift is something added to the function. If it's positive, it shifts the function up. If it's negative, it shifts the function down. So here we have an example, and I have to say this is one of the worst graphs I've ever seen. Look at, it looks really wide. It's not. Right? A is 1 here. The reason it looks wide is because of the scale. I have no idea why you would use such a different scale on the x and the y. Don't do that. All right? Don't ever do that. But I borrowed the graph. I didn't graph the graph because that makes me cringe. But we can still talk about the translations even though it's a lousy graph. So vertical translation, when a number k is added to f of x, the graph will shift vertically. So here we have our parent function, f of x equals x squared, has a vertex at 0, 0. If we add 5 to that function, we have f of x equals x squared plus 5. Notice that the whole graph shifts up 5 units. And now the vertex is at 0, 5. And not only the vertex, but every point will shift up 5 units. Right? And on Desmos, you can take a look at this. Right? That might be something you want to go back and put into those sliders, add 5 and see what happens. Right? So it's a great way, that Desmos activity, you can go back to it. It will remain open all year, and you can add values in to the x, to the whole function, and see exactly what happens. Right? So this example shows a vertical shift of the parent function, f of x equals x squared, up 5 units. So adding to f of x shifts the function up. Subtracting from f of x shifts the function down. Right, so here we have the blue graph is y equals x squared, f of x or y equals x squared. I put the points there because it's the parent function. It doesn't have many useful points. Its vertex, x-intercept, and y-intercept are all the exact same value, 0, 0. So we get nothing from this graph. So a table of values helps on this one because we can't solve for any more points than 1. All right, so here, and we'll use that same table to graph f of x equals x squared as the parent function, and use that we'll shift that parent function to graph. You don't have to ever write that table of values down unless you choose to, because it certainly is easy enough to remember. If we square negative 3, we get 9. If we square negative 2, we get 4. If we square negative 1, we get 1. If we square 0, we get 0. If we square 1, we get 1. If we square 2, we get 4. And if we square 3, we get 9. And you might think, why did I only use those 7 values? How about some more? Because if I square 4 or negative 4, I get 16, and that's usually right off my graph. So that's the reason we stopped at negative 3 and 3. It fits on the graph. All right, so what if we have the graph f of x plus 1. In other words, we add 1 to x squared. Well, notice now that the vertex is at the point 0, 1. Right, so our vertex, as well as all the other points, have been shifted up 1. And you could compare another point to see that that's true. Right, so here's the point 1, 1. If I just follow 1 up till I get to the red graph, I see we have the point 1, 2. Right, so every point on the parent function has shifted 1 upwards when we graph f of x equals x squared plus 1. So adding 1 to the whole function is going to shift the graph 1 unit up. Here we add the green graph is f of x minus 3. In other words, we've subtracted 3 from the parent function. That gives us f of x equals x squared minus 3. Notice that the vertex is now at 0, negative 3. Right? So it's 3 units less. And not only the vertex, but every point. Right? So here's the point 1, negative 2. Right? So it's 3 units. What happened to the, we have 1, and I don't know. 1 comma, how about the 1 there? So if we were to subtract 3 from 1, we would get negative 2. So every point on y equals x squared has been shifted 3 units down to graph f of x equals x squared minus 3. So subtracting 3 from our function will shift the graph 3 units down. Okay, so as you can see, a number added or subtracted from a function will cause a vertical shift or translation in the function. Here's the absolute value function I promised you. All right, so you see it looks an awful lot like a parabola, except it's a v instead of a u. So f of x equals the absolute value of x. All absolute value bars do is turn the number positive. Right, so here we have the points negative 3, 3, negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2, 3, 3. Right, so whatever I plug into the absolute value bars, the output is just that same number but positive. Right, so if we look at f of x equals the absolute value of x, has a vertex at 0, 0. What about if we add 2 to that function? Right, that would give us f of x equals the absolute value of x plus 2. Notice that 2 is not in the absolute value bars because the 2 is added to the whole function. So if we add 2 to the whole function, we now have the vertex 0, 2. Notice that vertex has been shifted up 2 units, but not just the vertex, of course, every point. So here, for example, we have the point 1, 1, a point in a parabola, and a point that f of x equals x squared and f of x equals the absolute value of x have in common. Whether you square 1 or you take the absolute value of 1, it's still 1. If we follow that 1 up to the red graph, we have the point 1, 3. Notice it's 2 more, right? And that's because the graph has shifted. Let me make that nicer. Shifted the graph up 2 units. So if we add 2 to our function, that will shift the graph up 2 units. I don't know why I didn't just write the number there. What if we subtract 4 from the absolute value bars? Right, so we have f of x minus 4, which would be the absolute value of x minus 4. Notice again that minus 4 is not in the absolute value bars because we're subtracting that from the whole function, not from the x. Notice that will change the vertex here to 0, negative 4. Right, so again, the vertex has shifted. Right? And in this case, the vertex is shifted down 4 units, but not just the vertex. All the points have shifted down 4 units. All right, so instead of 1, 1, we have the point 1, negative 3. All right, so if we subtract 4 from our function, that will shift the graph down 4 units. All right, so the graph f of x plus k, where k is any real number, is the graph of f of x, but vertically shifted by k. If k is positive, it will shift up. If k is negative, it will shift down. So notice in vertex form, it's called x minus h squared and then plus k. So it's plus k all the time. Doesn't have to just be a parabola. All right, so now let's see if we can use vertical translations to shift a parent function and graph the function f of x equals x squared plus 3. And you have this one in your notes. All right, and so we're going to go through all the different possibilities here. All right, so first of all, let's graph the parent function. And that got erased from mine up here. I don't think, oh, it's not on yours either. All right, so let's add that. So first thing we're going to do in your notes, put in number 1, graph y equals x squared. Right. I'll write the points down on this one, and then I don't have to write them again, and you don't have to write them again. All right, so x and y, if we have negative 3 squared is 9. If we have negative 2 squared is 4. Negative 1 squared is 1. 0 squared, of course, is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. I go through that pretty quickly because it's just not that hard to square those numbers. All right, and so now we're going to graph those exact points. So 0, 0, 1, 1, and negative 1, 1. And 1, 2, 3, 2, 4, and negative 2, 4. And then 3, 9. So that's 4, 5, 6, 7, 8, 9. And negative 3, positive 9. All right, and you can see why I didn't use 4 and negative 4 because, like I said, they're going to go off right off the graph. And these are plenty of points. So now we're going to connect our points with a nice smooth curve. And we have graphed the parent function y equals x squared. And we're going to use that parent function to graph f of x equals x squared plus 3. And notice the format of that function. This is a function we could graph with translations. So we're going to go through our different shifts and see what we would write down. Horizontal shift. Right? Well, we haven't even talked about horizontal shifts, and that's because we haven't gotten to any yet. And this graph, likewise, does not have a horizontal shift. I will tell you that a horizontal shift is something we add to x. And you should have seen that in the Desmos activity, right? What happened when you added a positive or a negative number to x. But in this case, nothing is added to x. So for horizontal shift, we are going to write none. And you should write none as well. All right, so vertical shift, we're adding 3 units to our function. So that means our function is just going to be the same as the parent function, but shifted up 3 units. All right, so you already have the blanks filled in. I don't, because I wanted to kind of go over it with you, but I already filled them in for you. So it means we do have a vertical shift. Because we added 3 to the whole function, our graph is going to shift up 3 units. Right? That's going to change our vertex. So here, the vertex for the parent function is 0, 0. If we add 3 to the y, it means the vertex is going to be the point 0, 3. And we'll see that when we shift the graph. Speaking of that, why don't we shift the graph now? And then we'll talk about domain and range. All right, so we're going to take every point on this function, all 7 of them, and just shift them up 3. Right? So that means that we'll start off to the left. All right, so negative 3, 9 is going to shift up 3. Right, so that's now it's at negative 3, 12. Negative 2, 4 is going to shift up 3, so now it's at negative 2, 7. Negative 1, 1 is going to shift up 3, so now it's negative 1, 4. 0, 0 is going to shift up 3, and notice it's now 0, 3. Right? 1, 1 is going to shift up 3, so now it's going to be 1, 4, and 2, 4 will shift up 3, that'll be 2, 7, and 3, 9 will shift up 3, now it's going to be at 3, 12. So we've just taken the points that an easy graph, y equals x squared, and taken all our points and shifted up 3. Right, that makes this graph a lot easier to graph, because if we were solving for x-intercepts, vertex, and y-intercept, well, guess what? Y-intercept and vertex are the exact same thing, and there's no x-intercepts. Right? We'd have 1 point. But we would have to create a table of values. Notice I didn't plug anything into the function. All I did was I took the parent graph and shifted it up 3. Because if I add 3 to y equals x squared, I'm going to have the same graph, just shift it up 3. All right, so adding to the function is going to shift the function up. Subtracting from the function shifts the function down. I hope you can see that, because for me it's on the gray. I'll move it up a little bit. So domain and range are the last things we're going to fill in. The domain, doesn't matter what this parabola was, it's going to be negative infinity to infinity. All the time the domain for a quadratic, matter of fact the domain for any polynomial, is negative infinity to infinity. And the range, right, so that's our y values. The range for the parent graph was 0, 0. Was 0, infinity. The range for the red graph, let's label that red graph, f of x equals x squared plus 3. There's really no reason for those parentheses, by the way. I guess they really want to show you that it's not added to x. Right, so the range for f of x equals x squared plus 3, our low y value is now the point 3. So that means the range is 3, infinity. Right, so we've not only changed our graph and changed our vertex, we've changed our range. Change your vertex, you'll change the range. All right, I'm going to stop here, and I'm going to do horizontal shifts on the next video. All right, bye for now. Yep, we're up to horizontal.